Okay, cool. So for those of you listening remotely, my microphone is running dangerously low on batteries, and so it's likely that you will only be able to hear the first few minutes of this course. But you know, I've got it on like HD video mode, so hopefully you can lip read. Okay, for the rest of you, so let's sort of maybe take brief stock of where we left off last time. So we were studying these really simple like sanity checks on models, marginal guarantees, get the mean right on average, get the quantile right on average. And we started thinking about these not just in a setting in which there was a distribution where it really makes sense to talk about means and quantiles, but even in like a sequential setting where remember what the sequential setting is. There is not necessarily any distribution, but rather there's an adversary. Every day you have to predict something like the mean or the quantile of you know, of who knows what. There's no distribution. But then, you know, after you make your prediction of a mean and a quantile, a number shows up, the label. And the number could have been chosen by any process. We're making no distributional assumptions about it. And the goal that we set out for ourselves was that in the worst case over sequences, in the worst case over adversaries who might be producing the sequence of numbers, it should be the case that empirically over the distribution that's defined ex post, like the empirical distribution over the sequence that actually shows up, that our predictions satisfied the marginal conditions that we wanted, like marginal mean consistency. And we defined, but did not see how to solve the problem of having these sequences satisfy marginal quantile consistency. Okay, and so roughly here's what I want to do today. So first of all, I want to finish up the sequential setting for these simple marginal guarantees. Okay, so last time we saw how to satisfy marginal mean consistency even against an adversary. It was actually super simple. And I also want to show you how to satisfy marginal quantile consistency against an adversary. And maybe one thing that I want to point out, you know, we'll derive some simple little theorems, but it's to the for the point of driving home that solving these problems in the sequential setting is like in a formal sense, like strictly harder than solving these problems in the distributional setting. It's not like they're like incomparable, it's harder. And the way we'll demonstrate that is we'll give reductions. We'll say, suppose you give me any method to, you know, satisfy marginal mean consistency or marginal quantile consistency against an adversary. Well, you know, if there is a distribution and I can sample from it, then I can just reduce to this method for solving the problem against an adversary to do the same thing we did sort of from simple first principles in the distributional setting, to take an arbitrary model and then by reduction to these sequential algorithms, like patch it up so that it satisfies marginal mean or quantile consistency against on the underlying distribution. And sometimes for quantiles, you'll need randomization, and this will also be your introduction to another useful probabilistic tool called Azuma's inequality. Okay, so we're going to do that. And then finally, I want to move on beyond these like marginal conditions, and I want to tell you about calibration. And we'll start off and probably, this class not get past it, but we'll start off again in the batch setting. Right, we'll say, okay, there is a distribution. We can take samples from it, perhaps. We can estimate expectations over this distribution. And what I'd like to do is start with an arbitrary model, just as we did in the, you know, in studying marginal quantities, and somehow, like, hopefully in a way that's not too complicated, patch it up so that it is calibrated, and also so that we've only improved the model. So we want that our new model should be, you know, more calibrated than the one we started with, you know, ideally perfectly calibrated. We'll see what that means, but it should also be more accurate. Okay, and more accurate will be measured by squared error when we're talking about mean calibration, and we'll see it also makes sense to define quantile calibration, and more accurate there will be in terms of pinball loss. Okay, so that's roughly the plan for today. questions about any of the broad outline before we start? Okay, so let me first remind you of some definitions. In particular, I'm going to start by talking about the sequential setting. So let me remind you what we mean by mean and quantile marginal consistency in the sequential setting. Okay, just review from last time. So remember, in the sequential setting, what our algorithms are doing is they're generating transcripts. Okay, so we'll fix a transcript. Call it pi, and all pi is it's a record for each of the time steps of the feature vector that showed up at that time step, the prediction that our algorithm made at that time step, and the label that showed up at that time step, and the number of time steps with capital T. Okay, so remember in the sequential setting, we see a feature vector, but not a label. We need to make a prediction, and only then do we learn the label. Okay. We say that pi satisfies marginal mean consistency with error alpha if, when I look at the empirical distribution that exists ex post after the transcript has been realized, so just the uniform distribution over xt, yt, my predictions pt satisfy marginal mean consistency as we were used to thinking about it on distributions. So in particular, if I look at the average of my predictions, and I compare that to the average of the labels, well, if I satisfied marginal mean consistency, those should be exactly equal, and they should have error alpha if I have alpha error. Okay, so just, my predictions should equal the labels on average, as measured on the empirical distribution that was generated by my algorithm. And we want that this should be the case, like, we want to design algorithms so that this is the case in the worst case over adversaries, and so it should hold uniformly over all possible sequences that might be generated. Similarly, we can say that pi satisfies marginal quantile consistency with respect to some quantile q and with error alpha if, again, when I look at the empirical distribution on the realized transcript and I compute how frequently it was the case that the label was actually less than my prediction, compare that to Q. Well, if these really were drawn from some distribution and I was predicting a Qth quantile, these should really ideally be the same thing. And we'll say that I have quantile consistency error alpha if the difference is not 0, but alpha. Okay. Now, if you recall last time, we saw an algorithm for promising that against any sequence, we would satisfy marginal mean consistency that had actually extremely low error. If we saw a sequence of length 1 over t, the marginal mean consistency error was 1 over t. Can anyone remind me of what this very silly algorithm was? How do I satisfy marginal mean consistency against? Yeah, so say I'm a weather predictor, I'm supposed to predict the chance of rain. If it rained yesterday, I will predict a 100% chance of rain today. If it did not rain yesterday, I will predict a 0% chance of rain today. Okay, so the algorithm was, I don't know, silly mean predictor. We just hallucinate that at day 0, it did not rain. For each day, we observe, a whole bunch of meteorological observations, xt, and trash them. We just throw them away. Who needs meteorological observations? We predict that what's going to happen today is with certainty what happened yesterday. Okay, if it rained yesterday, 100% chance of rain today. If it didn't, 0% chance of rain today. And we observe the outcome. Okay, and the theorem we proved was that for any sequence of examples, silly mean predictor generates a transcript that satisfies marginal mean consistency with error alpha at most 1/t. Okay. And the analysis was very simple, like what's the difference between our predictions on average and the outcomes? Well, our predictions are just shifted over from the outcomes by 1. And so, it's just whether it rained on the last day or not that is our error. Okay, and so to recall, like maybe you should have, upon seeing this algorithm, you should have thought to yourself, gee, like if I can satisfy marginal mean consistency against, maybe originally I was scared of adversaries and maybe, thought well of marginal mean consistency. This should make you less scared of adversaries and make you think less well of marginal mean consistency. It's too easy to satisfy. Okay. But I do want to, and both of those things are true. You should be less scared of adversaries. You should not admire marginal mean consistency. But I do want to point out, and again, it's not very complicated for this example, but this will be a theme throughout the course, that in general, although these online algorithms can look silly as this one does, and we'll see they can look even sillier for quantile estimation, the online adversarial setting is stronger than the batch setting. Okay, so there's a very concrete reduction that in this case is very simple, but we'll see as a theme throughout the course that there's always a reduction of this sort that sort of says, look, if you've got an algorithm that has some guarantee like this in the sequential setting, you can turn it into an algorithm that has the same guarantee in the batch setting. So the sequential setting is strictly more difficult than the batch setting. Okay, so let's sort of maybe state that reduction. Here's a particular algorithm, but like the reduction is agnostic to what algorithm you're using. It's going to say any algorithm that can promise alpha approximate marginal mean consistency against an adversary can be used to, in a distributional setting, patch up a model that previously had some marginal mean consistency error, and the fixed model won't. Okay, so here's the theorem. So suppose A is such that when run against an adversary for T rounds, generates a transcript pi. That satisfies marginal mean consistency. With error at most alpha. Okay, so we've got this algorithm in the sequential setting. Maybe it looks something like this. Now, let's go back to the batch setting. Okay, so suppose we've got some model, maps features, so labels, and a data distribution. And suppose it's the case that, perhaps F does not satisfy marginal mean consistency on this distribution, and we wish it did. Okay. Let's consider the following reduction whose goal, that has the goal of taking F, somehow applying our algorithm A to come up with a way to fix F to have marginal mean consistency on the distribution. Well, how should we do that? Well, how do we interact with a sequential algorithm? We take the role of the adversary, right? Like the sequential algorithm is expecting to get some Y every day. If we can feed it a Y every day, it'll spit back a P every day. And so like our goal in trying to use the algorithm as a subroutine is to take the role of the adversary and feed it Ys. Well, what are some good Ys to feed it? Well, at each round T, what we can do is sample a new point, call it X hat T, Y hat T, from this underlying distribution. And then, wearing our adversary hat, feed our sequential algorithm, feed A, the example that we'll call XTYT, which is just what we get when we replace the label Y hat T with Y hat T minus F of X hat T. It's just the residual, the difference between the label and what our model thought the label was for that point. Okay, so this results in some transcript. And remember, a transcript is a sequence consisting of XTs, PTs, and YTs. Now we picked the XTs and the YTs, those aren't so interesting, but the PTs were generated by the algorithm. Okay, let's let delta just be the average of the PTs. The average of the predictions of the algorithm over the sequence. And let's let F hat of X be the new model defined as F of X plus delta. Okay. Then, with probability 1 minus delta, this is over the randomness of the examples we picked, F hat satisfies, let's say, alpha prime approximate marginal mean consistency, where alpha prime is at most alpha, whatever the marginal mean consistency guarantee of the algorithm was. We've got an algorithm that can make that really small, 1/t, plus, the inevitable statistical estimation error, which is a term that you've seen before, comes out of Hoeffding's inequality that looks like this. Okay, so not a terribly surprising theorem. We've seen how to more directly, of course, satisfy marginal mean consistency from samples with error that looks like this. But this is to point out that, like when you have a sequential algorithm that has guarantees against adversaries, you can run it on any sequence you want. You can run it on sequences that are drawn from distributions, and the result will be generally something you can translate into a statement about the batch setting. Yeah.
I'm sorry, could you possibly explain again why we are feeding the residual to simulate adversary?
What do you think would be better to feed?
I have no idea.
Okay, so let's see. So our goal is to, patch up some model F, which might be some complicated thing. So somehow, so maybe the first observation is that we'd better feed the thing we feed to the algorithm better have something to do with F. Otherwise, the algorithm will just have no insight into the object we're trying to fix up. But maybe the way to most directly see it is to say, okay, well, what does it mean that we're trying to come up with a model that has that is marginally mean consistent, which means that our hope is that the expectation of f of x on the distribution is equal to the expectation of the label, is equal to the expectation of y. Now, f hat of x is f of x plus delta, right? So if this thing is supposed to equal, the expectation of the label, that means delta should equal the expectation of the label minus the expectation of f of x. And so, the y that we're feeding into that is, well, it's y minus f of x. It's some random variable that in expectation is equal to what we want delta to be equal to. So maybe that's the most direct intuition, and we'll see that's exactly how we prove this, which is, again, just an application of Hoeffding's inequality to the right distribution. Does that make sense? Yeah. Good though, yeah. It is. That's not one of the requirements of marginal mean consistency. You're right that if the weatherman starts predicting a -% chance of rain, you might start to suspect maybe he doesn't know what he's doing. But if the only way you're testing him is through marginal mean consistency, he would still pass the test. So it's true that we might want to start asking for more stringent things, and later this lecture we'll see calibration, which does. That's right. And if you look at the guarantee or the analysis of this dumb algorithm over here, there's no requirement actually that the numbers that the numbers are non-negative, for example. Okay. So let's prove this. Yeah, and just sort of keeping in mind, maybe the form of this theorem, because we'll, as with all of these things, we'll see more complicated versions of them as we go on. This is our first baby, what's called offline to online reduction. You can solve the online problem, the sequential problem in particular, you can solve the offline problem, the distributional version. Okay, this one's especially easy. Okay, so what do we know? We don't know anything about this algorithm. It's not necessarily this particular algorithm. It's any algorithm guaranteed to satisfy marginal mean consistency. But we do know that the promise is that for any sequence of examples, in particular this sequence of examples, it outputs a transcript, in particular predictions that have marginal mean consistency error at most alpha. So what we know is that the transcript satisfies the following. If I average the predictions and compare them, the average of the labels, the difference is at most alpha. That's the definition of marginal mean consistency on a sequence. Okay. So let's let delta hat be the average of the y hat t minus f of x hat t quantities. Okay, the average of these quantities we sampled from the distribution and fed to the adversary as labels. Okay, delta hat is just right, like each of these terms is equal to the yt's as we've defined them. Okay, so just like rewriting what we have up here, right? The average of the pt's, that's what we call delta. The average of the yt's, that's now what we're calling delta hat, right? And so this is just saying, like this inequality is just saying that delta, the average of the pt's, differs from delta hat, the average of the yt's, which are each y hat t's minus f of x hat t's. These two quantities differ by at most alpha. Okay. Now, it's sort of easy to see that the expectation of delta hat, this is just equal to the expectation of a single sample taken from the underlying distribution of y minus f of x. Right, because each of these, y hat, x hat pairs are sampled from the underlying distribution, and we're just averaging over them. So, the expectation of each term is identical, and we're just averaging over them. Okay, so we're in a situation where we can apply Hufting's inequality, right? This probabilistic inequality we saw a couple classes ago, right? Like this quantity is an empirical average over t things, or it's a sum over t things, each of which has scale 1 over t. And its expectation is something simple. Okay, so this is exactly the kind of quantity that Hufting's inequality applies to. This is like, the empirical average of the points sampled from the distribution. This is their expectation over the distribution. Hufting's inequality tells us that with high probability, the empirical average is close to the expectation. Okay, so in particular, we can apply Hufting's inequality with some, the choice of our error parameter to be the square root of 2 log 2 over delta over t. If you recall, what Hufting's inequality says is the probability the empirical average differs from its expectation by more than epsilon is less than some quantity that, goes down exponentially in t, this is the choice of epsilon that makes the right-hand side of Hufting's inequality evaluate to delta. It's the choice that is going to give us a guarantee that holds with probability 1 minus delta. And so what we get when we want to interrogate the marginal mean consistency error of f hat is that, well, the difference between f hat of x and y, the absolute value difference on average, which is its marginal mean consistency error, is by definition the difference between f of x plus delta and y on average, because f hat of x is just f of x plus delta. And, we don't know that much about delta, but we know something about delta hat. And we know that delta and delta hat are close. So in particular, this is at most the difference between f hat of x plus delta hat and y plus maybe an additional error term alpha. Right, I just swapped out delta for delta hat, but I know from the guarantee of marginal mean consistency of the algorithm that delta and delta hat are within alpha of one another. And this is just the expectation of hat of x plus the expectation delta hat plus delta hat minus the expectation of delta hat minus y plus alpha. All I've done is I've added the expectation of delta hat and then subtracted it off again. And the expectation of delta hat is y minus f of x. So the expectation of alpha hat cancels out f of x, the f of x minus y term in this expectation. And all that is left is the absolute value difference of delta hat minus the expectation of delta hat. And this is the thing that's bounded by Hufting's inequality. With probability 1 minus delta is at most epsilon. Right, so this by Hufting with probability 1 minus delta is at most alpha plus the square root of 2 log 2 over delta over t. Okay, so if we have an algorithm that promises it can achieve marginal mean consistency against an arbitrary adversary, in particular, it can help us do what we want to do on a distribution as well. Okay. Yep.
Is there a reason to do like Huffington inequality or not inequality?
People are not always clear on what they mean when they say Hufting versus Chernoff. I think for the purposes of this class, Hufting is the one that gives the additive bound and Chernoff gives the multiplicative bound. The additive bound is what we want. Okay. So let's think about quantiles now. So I want to, again, do the same thing for quantiles. So I want to first show that if we want marginal quantile consistency, we didn't need to assume a distribution. There's an algorithm that can promise us marginal quantile consistency, with probability 1 against an arbitrary adversary, and then also observe that for quantile estimation as well, the sequential problem against an adversary is only more difficult than the distributional problem, and that there's a very similar reduction from the distributional problem to the sequential problem, with one notable difference. The reduction to the sequential problem for quantiles is going to involve randomization. We're going to have to come up with a randomized predictor at the end. But let's start with the algorithm. And yeah, there's actually two algorithms I could show you for marginal quantile consistency, one dumber than the other. And I'm going to show you the less dumb algorithm. But maybe we can brainstorm on the more dumb algorithm first. So the algorithm for marginal mean consistency was kind of dumb in that, like, it looked at the data, but just predicted what happened yesterday. I claim there's actually an algorithm for marginal quantile consistency. Right, so for marginal mean consistency, we threw out the meteorological data, but at least we paid attention to like when it rained or not, because we had to predict that what was going to happen today was what happened yesterday. I claim for marginal quantile consistency, there's an algorithm that can throw out the meteorological data and also the labels. You don't even have to like look out your window and see whether it rained. Can anyone tell me if I want to predict what look like marginally, at least, that I'm predicting the 90th percentile of some distribution, how I can do so? Let's say. That's right. Yes. So remember, what is the goal of marginal quantile consistency? Every day I should come up with some like threshold, and what I'm checking for is that the fraction of days for which the label is below the threshold is supposed to be Q. So one way I could do that without looking either at the features X or even the labels Y is just for a Q fraction of rounds, or for every, I'll just repeatedly do the following. For like a Q fraction of rounds, I'll predict the highest possible label, let's say 1. And for the remaining, I'll predict the lowest possible label, let's say 0. Right, so like by construction, I will I will predict something larger than the label a Q fraction of the time and something smaller than the label a 1 minus Q fraction of the time. I will satisfy marginal quantile consistency. In fact, the rate at which, my quantile consistency error goes to 0 will be 1 over t. It'll be like as fast as you could possibly hope for. And yet, like, it's even dumber than the mean algorithm because it's like entirely independent of the data. Okay, so I want to point that out because, I think that really gets at the weakness of these marginal definitions. But let me instead present to you a different algorithm, which doesn't distinguish itself by the theorem we're going to prove. The theorem we're going to prove about it, we could have proved about this dumber algorithm, but it's doing something a little bit more sensible, and is something that actually, appears in the, there's a paper about this, and a conformal prediction paper, and it has reasonable empirical results. So let me show you this sort of more clever algorithm that doesn't, has the same theorem we could have proven about the dumb algorithm, but this one looks at the data. Okay. So let's call this online marginal quantile predictor. And it'll take as input a target quantile Q and a learning rate eta. And here's what it does. So the first prediction we're going to make is going to be 0, let's say. And then in rounds, indexed by little t from 1 to capital T, we will observe all of the features for today, all of the carefully gathered meteorological measurements. And as with our mean predictor, we'll ignore these. Who needs data? But at least we're going to pay attention to the actual outcomes. Okay, we'll predict PT. Really, that's just 0. And we'll observe YT. Okay, and then we're actually going to look at what we observed and do something different as a function of it. We'll let tomorrow's prediction be equal to today's prediction plus an update. We'll change it by some multiple of eta, our learning rate. And what is that multiple of eta? It's Q, our target quantile, minus the indicator of whether our prediction today was bigger than the label today. Okay. So that's it. So what's happening, we're sort of maintaining a slowly moving prediction. We're moving it up or down as we see evidence. When we cover the label, okay, when we predict something that covers the label, that's supposed to happen at Q fraction of the time, then we will reduce our prediction by 1 minus Q. And when we fail to cover the label, that's supposed to happen at Q fraction of the time, we'll increase our prediction by Q. By all of these increases are mediated by the learning rate. We'll increase it by eta times Q, or we'll decrease it by eta times 1 minus Q. Okay, so we're moving our prediction up or down depending on whether we failed to cover the label. But how much we move it up rather than down depends on our target quantile. Okay, does this make sense? And if you've seen it before, you might recognize this as a more general algorithm called online gradient descent, which can, in general, optimize convex loss functions in the sequential setting. In this case, applied to the pinball loss. So this is an update based on the gradient of the pinball loss of our prediction, but we're going to analyze it as a one-off. Like in this particular setting, there's an extremely simple analysis, but just for culture, you can also think about this as an instantiation of a more general algorithm for minimizing adversarially chosen convex loss functions by basically adding some multiple of the gradient of the loss function today. And it works for the more general problem as well. Okay. So what can we say about this algorithm? So for any sequence, examples of length t, any target quantile q between 0 and 1, and any learning rate eta, let's say greater than 0, this algorithm, online marginal quantile predictor, produces a transcript satisfying alpha approximate marginal quantile consistency, where alpha is at most, let's say, 1 plus eta over eta times t. Okay, so if eta is a constant, then this is sort of the same 1 over t rate we get for marginal mean consistency. Okay, and you could imagine that, you know, if you wanted to run this algorithm like in practice on data that wasn't truly adversarial, and you wanted to get like reasonable answers, you might want to set eta to be something small, right? Like if eta is something small, then what's this sort of doing? It's, you know, kind of just like empirically creeping up to the right quantile, moving around a little bit, you know, tracking it. So maybe if the distribution's shifting, it'll like move to like another quantile, but like it's not jumping around wildly. And in fact, you can prove a more refined theorem of that sort about this algorithm that you couldn't prove about the super dumb algorithm that like closes its eyes and ignores the data, that if the data is coming from a distribution, this thing will find for small eta something that is sort of consistently around the right quantile. And even if that distribution is shifting, so long as it's not shifting too quickly, it will track the correct quantile. Okay, so that's a theorem that's not too hard to prove about the same algorithm. But in particular, you know, you always get this worst case guarantee, even if there is no distribution. Okay. So let's stare at the update rule, right? How are we going to prove this theorem? Right, the update rule is written as, you know, what is tomorrow's prediction as a function of today's prediction, and like the indicator of whether today's prediction was bigger or smaller than the label. But we can solve instead for something else. We can solve for the indicator of whether today's prediction was bigger or smaller than the label, and you can get an expression in terms of the other quantities, right? So just solving for this indicator function instead of tomorrow's prediction, what we get is that the indicator for whether yt was less than or equal to pt, well, that's just q minus pt plus 1 minus pt over eta. Okay, right. So we can, you know, the indicator for whether today was covered by the, you know, whether today's label was smaller than our predicted quantile. You know, if this was really stochastic, you might wonder, like, how can I write such a thing in terms of like known quantities, because it's like a random variable. But one of those known quantities is my prediction tomorrow. So there's no problem here, right? Right, so this is just taking the update rule and solving for a different variable. And this is a convenient, oh, yeah. Good. Good. So this is a convenient form for the update rule, because remember, what am I interested in when I am thinking about marginal quantile consistency? I'm interested in how frequently this event occurs. I'm interested in the average of this indicator over all of the t rounds. Okay, so what's that? What fraction of the rounds is it the case that I cover the label? Is it the case that yt is at most pt? Well, I have an expression for that, right? I can average over the right-hand side. So, okay, first I'll average over q, but that's just a constant, so that's just q. And then I'll average over this. I'll take out the 1 over eta. So I get 1 over eta times t times the sum from t equals 1 to capital T over all of the rounds of pt plus 1 minus pt. Okay. Now this is a telescoping sum, right? So most of the terms cancel out. And I get just q minus pt plus 1 minus p1, just the last term in the sequence minus the first term in the sequence over eta t. And p1 was 0, so this is just q minus pt plus 1 over eta t. Now I claim that for all time steps t, the prediction that I make is never bigger than 1 plus eta. Okay? And let's think about that, right? Like these predictions are fluctuating upwards and downwards, but whenever I cover the label, whenever I predict something that's bigger than the label, I move downwards, right? So if my prediction today was anything bigger than 1, then I'm not going to increase it tomorrow, right? If my prediction today was bigger than 1, my prediction tomorrow is going to be less than my prediction today, because the only option is that my prediction was bigger than the label and my update's going to move downwards. So to think about what's the biggest prediction this algorithm might ever make, all I need to do is to think about, what's the biggest increase that this algorithm will ever make to its prediction between today and tomorrow, right? Because what must happen, but like the worst case is that my prediction was, 1 minus epsilon today, and then, miracle of miracles, I covered the label, and my prediction moved upwards by as much as possible. But the largest amount my prediction can move upwards is eta, right? The learning rate controls, right? Like, the thing inside here, the thing inside the parentheses here is always a number that is at most 1. So the increase in my predictions at most eta, and so my prediction at any moment can be at most 1 plus eta. And so this is at most q minus 1 plus eta over eta t, which is what we wanted. Okay, that makes sense. And by the way, like you might have thought, should I just cap it at 1, right? Like maybe don't let it go above 1, but and you could still analyze the algorithm by doing more work if you did that. But that would have really messed up this clean expansion here, because I guess greater than or equal to this, and similarly or no. That's right. And then I guess similarly, it's less than or equal to q. Right. So if you kept things at 1, it would have made the analysis like a lot less convenient, because you wouldn't have been able to get this nice telescoping sum. But you could have still analyzed it as online gradient descent if you wanted to. Okay, so that's marginal quantile consistency against an adversary. And by the way, like unlike the mean-based algorithm, which I showed you, which like truly is a dumb algorithm to run, and unlike the even dumber algorithm I told you about for quantiles that like ignores the labels and just predicts 1 with probability q and 0 otherwise, this one's actually like a pretty good algorithm. Like you can, like this is an algorithm people use. You can evaluate it on real data and sort of one of the state-of-the-art algorithms for what's called sequential conformal prediction. We'll get to conformal prediction in a few lectures. In settings where there is distribution shift. And sort of the reason this is a sensible algorithm is that in addition to having these sort of worst case guarantees, weak though they might be, the algorithm's actually doing something very sensible if you believe there is a distribution that might just be changing, right? It's actually sort of correctly tracking the quantiles, and so long as it doesn't change too quickly, it'll track them as it goes on. Okay. Okay. Let me prove one more thing about these sequential algorithms before we move on to calibration. And what I want to do is I want to give the online to offline reduction for quantile marginal mean consistency. In particular, I want to say, if you have any algorithm for promising quantile, marginal quantile consistency in the sequential setting, this one or any other one, you can use that to solve the problem of patching up an existing model in the distributional setting to make it marginally quantile consistent in the distributional setting. But there is going to be a sort of qualitative distinction between the reduction we see for quantiles and the reduction we saw for means, which is that the output of the reduction that we get here from the sequential to the distributional setting will be randomized. It'll be a randomized predictor, not a deterministic one. Okay, so let's see. Let me try to update this theorem to say what we want. Suppose A is such that when run against an adversary for T rounds, generates a transcript pi that satisfies marginal quantile consistency with respect to some quantile Q with error at most alpha. Okay, and suppose we've got some model and a distribution, and maybe our model F isn't sufficiently quantile consistent. And on this distribution, we'd like to patch it up. Let's consider the following reduction. So we'll do the same thing. We'll sample an example from the distribution, and the number we will pass at round T to our algorithm for marginal quantile consistency will be just, we'll transform the label in exactly the same way. We'll feed it the true label of our sampled example y minus the predicted quantile f of xt. And then we get a transcript. And here's now going to be the difference. So it no longer makes sense to set delta, the amount that we're going to shift the model by, to be the average of the predicted quantiles, right? Because means are linear, but quantiles are not, right? If I have, if I have a bunch of distributions and a bunch of sort of, say 90th percentile quantiles for those distributions. If I take the average of the distributions and the average of the 90th percentile quantiles, I don't have a 90th percentile quantile of the average distribution anymore. So we're going to define delta differently. Delta is going to be a random variable now. Let's let delta be uniformly distributed over the set of predictions P1, P2, or PT. Okay, so instead of letting delta be the average of these predictions, delta is going to be a random variable that is uniformly distributed over the predictions that were actually made. So then we're now going to define a model f hat. It's going to be a randomized model. F hat of x is just f of x plus delta as before, except delta is a random variable. Now we're sort of shifting f by a random amount. The claim is that f hat on the distribution has low marginal quantile consistency error. And just because I haven't really defined what that means yet for like a randomized model, let me just write out exactly what I mean. What I mean is that when I look at the probability now over two things, the probability both over the randomness of an example drawn from the distribution, but also over the randomness of delta, that the realized label is at most f hat of x, which is f of x plus delta, but now both the left-hand side and the right-hand side of this inequality are random variables, that this differs from Q by at most alpha, the marginal quantile consistency error of the sequential algorithm, plus the same term we had before, 2 square root of 2 log 2 over delta over t. This holds with probability 1 minus delta. Yes. Okay. So very similar theorem to before, but with some twists, a twist in the statement and a twist in the proof. Okay, so the twist in the statement is that when we switch from means to quantiles, our reduction is no longer deterministic. We can't just sort of shift the model by an amount that we get by averaging over the predictions of the sequential algorithm. We have to shift the model by a random amount that we get by randomizing over the predictions of the algorithms. And the twist in the proof is going to be that, like when we proved this theorem for means, this quantity delta that we analyzed was the sum of a bunch of IID random variables, and we could apply Hufting's inequality. The thing that we need to analyze here is not the sum of independent random variables for a reason we'll see. And so this, we'll get exactly the same bound, the same thing will be true, but we'll need to use a fancier probabilistic inequality that we will, again, see here for the first time, but probably not for the last time, called Azuma's inequality that lets us talk about martingales. Okay, questions about the statement of the theorem, though? All right, let's prove it. I bring special chalk and I don't want to accidentally use like the shit chalk that they supply us with here. Ira tipped me off to the special chalk. Okay. Okay, so what do we know? We know that our transcript satisfies alpha approximate marginal quantile consistency. Okay, so that means that if I average over all of the rounds, the event, the indicator for the event, that I predicted something, or the algorithm predicted something bigger than the label, that average frequency differs from my target frequency Q by at most alpha. And remembering how our reduction works and what the definition of Y is, this just means averaging over all of the rounds of the event that Y hat, the actual label drawn from the distribution, minus F of X hat, the prediction that my model gives for that label, this fell below the prediction with frequency at most alpha. Okay. So let's so we're sort of going to be interested in analyzing something about a distribution over labels that look like this, look like the residuals, the difference between the real label and the predictions. So let's define such a distribution. Let's let D prime be the distribution over residuals, the distribution over values Y minus F of X, where the pair XY is drawn from our original distribution. And let's let capital F of X be the CDF of this distribution. Okay, so capital F of X is just the probability when we draw a label from this residual distribution D prime that Y is at most X. That's just the CDF of this distribution we've just defined. Okay. So what we want to show, what we want is to say that when I look at the average over all of the rounds of the CDF value of the prediction made at that round, that this should be around Q. That's sort of our target. We want to sort of say that, like, there is sort of like the sort of equivalent thing to show, right? For marginal mean consistency, we sort of argued the average of the predictions was equal to the average of the labels. Here, for quantiles, what we want to show is that the average quantile value of the predictions is equal to the target quantile. Okay. Our technical problem is that, let's see. Yeah, our technical problem is that the actual random variables that are sort of our empirical estimator. So these random variables that are the indicators for whether YT is less than PT, these are not independent random variables, right? Because, right, so if we wanted to apply Hufting's inequality, we'd sort of need to say, okay, we've got, a bunch, the sum or the average of a bunch of random variables that have the right expectation, they're independent, and therefore we can turn, the Hufting crank and get that they sort of are very likely to be close to their expectation. We sort of want to do the same thing for like these random variables, but these are not independent random variables because PT, the prediction we make at time t in the sequential setting in general and in the very particular algorithm we gave, explicitly depends on y1 through yt minus 1. Right? Like PT is a function of the previous realizations. And so this sequence of random variables that we would like to average over and say, you know, like converges to its expectation, it's not independent. So we can't apply Hufting's inequality. Okay, but all is not lost. All you need to do is like know Azuma's inequality. So here's Azuma's inequality. Once again, more important than the little thing we're proving is probably Azuma's inequality. So if you haven't seen this before, you know, remember it. It's very broadly useful. So this is a generalization of Hufting's inequality to a setting in which the variables are not independent, no longer IID. Okay. So let's let x1 through xn be random variables, be bounded random variables. Such that their absolute value is at most CI. So in the worst case over their realization, they don't take, you know, values that are giant or enormously giant or enormously tiny. But in particular, they don't have to be independent. And let's let x less than I, this notation, denote the prefix of the realizations of x1 through xi minus 1. Okay. Then I can still say for all t greater than 0 that the probability that the sum of the realizations of these random variables differs, well, not from its expectation, but from the sequence of conditional expectations conditioning on all of the previous random variables is small. So the thing that this will hew close to is the sum over all of the rounds of the expectation of xt conditioned on x less than t. Okay, so you know, the tth element of the sum condition, we're taking the expectation of like xt conditioning on the realization of all of the previous ones. Okay, and this thing, these two quantities are likely to be close. Okay, so the probability that this difference is larger than t is controlled by something very similar to what shows up in Hufting's inequality. 2 times e to the minus t squared over 2 times the sum over all of the rounds of the bounds CI squared. Okay. So it's, you know, the way to encode this is even if you don't have independence, you can still apply Hufting's inequality. It's just that rather than converging to like the unconditional expectation of the random variables, what you can say instead is that it is very unlikely that your realization will be very different from the sum of the conditional expectations of your random variables conditioning on the previous ones. Yeah, I guess like there's, you know, well, there's this awkward thing where t is both the index of summation and like this, so maybe like this one could be epsilon and yeah, something like that. Okay, so we can use this. So, okay. So PT, let's think about the sequential prediction algorithm, right? Like for any sequential algorithm, the choice the algorithm makes at day t, right? It can be a function of the previous labels, but has to be independent of the label that will be realized today, right? Like the choice, like I don't get to choose as a function of the label, and the adversary doesn't get to choose the label as a function of my choice. So what is true, even though these indicators are not independent random variables, the PTs depend on the previous, y t minus ones. What is true is that if I look at the expectation over yt of the indicator that yt is less than or equal to pt, once I condition on all of the previous realizations, which by the way is enough to make pt well defined, pt is a function of the previous realizations, what is true is that the expectation of this random variable is what I want it to be. The expectation of this random variable is just the CDF of the label distribution evaluated at PT. Right? It's just the probability that the label is drawn from PT. Okay. And so this is the quantity that I can now plug into Azuma's inequality, right? This is this conditional expectation is like one of the terms that my empirical average is going to converge to. And so in particular, let's see. All right, I'm going to erase this, but let's just remember that what I'm doing to get f of x is I'm adding the random variable delta to f that is just uniformly randomly chosen over the PTs. Okay, so I can apply Azuma's inequality, and I can get that the probability that the empirical average, the empirical frequency with which prediction PT was larger than the label, okay? That's the average of the realizations of these random variables. The probability that that differs from the sum of the conditional expectations of these random variables, which remember is just the CDF value of the prediction, the probability that this differs by more than the square root of 2 log 2 over delta over t is at most delta. This quantity is just what you need to choose to cause the right-hand side of Azuma's inequality to evaluate to delta. Okay. So remember, the fact that the algorithm was marginally mean consistent, that told us that, the empirical frequency with which we covered the label in the transcript, it was close to Q. But now we know that the average CDF value of our predictions was also close to Q, because these two things are close by Azuma's inequality. So in particular, it must also be that with probability 1 minus delta, the average of the CDF values of our predictions over all of the rounds is close to Q. In particular, well, the empirical values were alpha close to Q, and now we have this additional deviation due to Azuma's inequality. And so if we look at the thing that we want to bound, what is the difference between the probability that now on a new example drawn from the distribution and over the randomness of delta, that y, the realized label, is less than the predicted value, and look at its marginal quantile consistency error, which is just its deviation from Q. Well, we can separately evaluate the randomness of the example drawn from the distribution and the randomness of delta. And we understand the randomness of delta. Delta is just uniformly random choice of P1, P2, P3, all the way up to PT. Okay. So let's just write that out. For each value that delta might take, it takes that value with probability 1 over t. In which case, this expression for each of those values, right, we can like sum up over all of the values that delta might take and consider the probability now just over an example drawn from the distribution that y is less than or equal to f of x plus pt. And we can ask, how much does that deviate from Q? Well, this is just exactly the sum from t equals 1 to t of, well, what's the probability that y is less than f of x plus t pt? That's just the CDF of the distribution evaluated at PT. And this is exactly the quantity that we bounded up here. Okay, so the average, the marginal quantile consistency error now on the underlying distribution is bounded. Okay, so just as before, solving the sequential problem, solving the problem against an adversary, it's not just like a different problem than solving the distributional problem. It's like a strictly more difficult problem, right? Like if you have an algorithm for the sequential problem, you must also have an algorithm for the distributional version of the problem. The reverse is not true, right? Like in general, the distributional version is harder. Okay, all right. We've now finished marginal guarantees. why don't we take like a 15-minute break, and then we'll introduce calibration. So let's see, it's 3:11. Let's pretend it's 3:10 and come back at 3:25. Okay. So marginal guarantees, very, very weak. Let's think about how else we might evaluate a model. So remember, okay, like if we're solving a regression problem, we might naturally evaluate just the accuracy of the model. Like a standard way to do that is with squared error that we've been calling B of F for Breyer score. And of course, you can check for, and so depending what you want to do, right? Like maybe a model that has low squared error is good enough for you. But on the other hand, maybe you were really hoping that this model had some probabilistic interpretation, like you wanted to use it to figure out what was your expected utility for various actions, for example. So you were really hoping to have learned this object we've called f star of x, the true conditional label expectation given the features x, and you're worried that your weather predictor is nowhere near that, is doing something like what we just showed they could be doing in the sequential setting, just predicting what happened yesterday. Okay, and if you're just checking for marginal mean consistency, you're not going to discover that. So what is something stronger that you can ask for? And calibration is one of the first stronger things you might think of, right? Especially after you've seen this ridiculous weather predictor that predicts 100% chance of rain if it rained yesterday, right? Like how can you notice that this ridiculous weather predictor is not predicting the truth? Well, it's that like frequently it predicts 100% chance of rain and then it does not rain on those days. And similarly, frequently it predicts a 0% chance of rain and then it does not rain on those days. So if you might notice that and say, aha, I don't think you know as much about weather as you're claiming to. And so calibration, generally speaking, will ask for a collection of sanity checks of that sort, right? It should be that if you predict 100% chance of rain, conditional on your prediction, it rains 100% of the time. If you predict a 0% chance of rain, it should be that conditional on your prediction, it rains 0% of the time. And similarly for anything else you might predict. If you predict a 30% chance of rain, it should rain 30% of the time. Okay, so calibration, if you squint at least, calibration should mean something like, if I look at the expected value of the label conditional on the event that you predicted this expectation to be V, then this should equal V. Okay, that sort of your the predictions should be correct on average, conditional on the predictions. So we want to satisfy basically marginal mean consistency, but now not just overall, but like also on the level sets of the predictor. So it's like a self-referential requirement, right? Like if I just predict the mean of the distribution as a constant function, then this is I might be calibrated and in a not very interesting way, right? Because there's only one level set of the predictor. And so the requirement is very weak. On the other hand, if I have a sophisticated predictor that's predicting all sorts of different things, this becomes a stronger condition. It's requiring that on every level set of the predictor, on which there might now be many, that my expectation, that sort of on average, my predictions have to be correct. Okay. Now there's a little bit of a problem here, which is that, maybe I never predict there's a 30% chance of rain. Maybe I predict there's a 30.012394629.3% chance of rain. And maybe I never do that twice. There's a lot of, a lot of small variations. And so like I want this conditioning event to make sense, right? Like as written, this could be conditioning on some like measure zero event. And like additionally, there's something else like, if I'm going to evaluate this eventually like empirically on data, I can't ask that like on data, something like this is exactly true. Right? If I flip 100 coins and the bias is 50%, it's not that exactly 50 of them are going to come up heads. There's going to be some variation, that depends on how many coins I flipped. And if I arrange things so that I never predicted the same exact prediction more than once, then, there'd be no way to falsify that I satisfy this condition, right? Like if I predict there's a 50% chance of rain exactly once, even if I'm correct, my like calibration error is going to be 0.5 because the empirical chance of rain over one day will be either 0 or 1. Okay, so like we're going to have to give some more nuanced definition than this. It's going to have to allow for variation, larger variation, basically when larger variation for smaller level sets of my predictor, when it just doesn't happen very often that I've predicted something, and I don't want to define things so that there's a way to like cheat basically and satisfy the definition just by making sure that I never predict the same thing twice. Okay, so so I'm going to give a couple of different definitions, but they're all designed to do these two things, to sort of simultaneously allow for larger variations when I'm averaging over smaller sets, and also to sort of stop someone from trying to cheat and have satisfy this definition of calibration just by making sure that whenever they predict a probability, they do it to 10 decimal places of precision so that, the conditioning event is very small. Okay, so first of all, because I want to like condition, like basically because I want to condition on like the level sets of this predictor, I'm going to talk about predictors that have finite range. I don't want predictors that are predicting like arbitrary real numbers. And when we learn calibrated predictors, we're going to algorithmically enforce this. Okay, so let's say that R of f will be our notation for the range of a predictor f. This is just the set of all values f of x that the predictor can take. For anything we might plug into it. Let's say that M is the cardinality of this range, and we'll always assume or enforce that M is finite. Okay. So what should be our measure of calibration error? I'll give 3 flavors of it, but these will all be flavors of what I'll call average calibration error. Okay. The first one I'll call K1, and it's a measure, you tell me a predictor and a distribution, and I'll tell you what your L1 calibration error is over this distribution. And it's just the sum over all of the values that your predictor might take, all of the values in its range, of the probability over a point sampled from the distribution that your predictor takes value v times the absolute value difference between v, the thing it is predicting here, and the actual conditional label distribution and the actual expectation of the label conditioned on the event that the prediction was V. Okay, so let's parse this. Okay, so first of all, like, this thing, right? It's like the quantity you'd expect if I defined calibration like this, right? Conditional on predicting V, the expectation of the label is supposed to be V. This is like the deviation from that. It's the difference between the expectation of the label conditioned on predicting V and V. If I was truly predicting the, if F was F star, if I was truly predicting the conditional label expectation given X, then this would be 0. For every V, I would have 0 calibration error. Okay. Now what I'm doing is I'm taking the average value of this, right? There's like sort of a different error term here for every level set, for every value V that might be predicted. And I'm computing the average of that over all of the level sets weighted by their size, weighted by how frequently the predictor predicts V. Okay, so this is sort of accomplishing the things we set out to do. First of all, if there's some tiny level set, if there was only one day when I predicted a 50% chance of rain out of 100 days, then even though my calibration error there is like going to have to be high because I predicted 0.5 and it either rained or it didn't. So like empirically, this expectation is going to be like 1 or 0. The weight there will only be 1 over 100. So it won't penalize me for high calibration error on small sets. On the other hand, I can't really cheat by like making sure that all of my 100 predictions were unique, because if I did that, my calibration, and I didn't know what I was talking about, my calibration error would be high for every single one of these sets. And so, I'm averaging over them, my overall like L1 calibration error would be high as well. Okay, so this is some measure of calibration error that tries to get at this, right? The expectation of the label conditional on my prediction should equal my prediction. That gives me slack for error on predictions that I make infrequently, so long as I do better on predictions that I make more frequently. And it's the average over these things. So if I do badly on every level set, then my average calibration error will be high. Okay, makes sense. Let's see. I'm gonna write down 3 more definitions that are all going to be similarly long, so I better prepare for this. Yeah. Yeah. The younger generation. Okay. So sometimes it's going to be more convenient to work with like a squared error variation of this, which I'll just call K2. Okay, which is like, to the extent that this is measuring like some L1 norm of calibration error, this is going to be measuring like an L2 norm of calibration error. This is also going to be a weighted average over all of the level sets of the predictor, weighted by the probability of that level set. But now instead of the absolute error between my prediction and the conditional label expectation, I'll take the squared error. So the difference between my prediction and the conditional label expectation squared. Okay, and it might sometimes be convenient to talk about the L infinity version of this as well, where instead of summing over all of the level sets, I'll take the maximum. Okay, so this is just the maximum overall of the level sets of the size of the level set. I'm still gonna scale down by the size of the level set times times the absolute value error between my prediction and the conditional label expectation given my prediction. Okay, makes sense. And I guess, right, so I'm still scaling down in this L infinity version because you sort of can't expect that, I get things right, certainly from samples on tiny level sets. These first two are not gameable by, predicting everything to 1,000,000 decimal points of precision, because even if all of the level sets are very small, if I have high error on all of them, that'll come out in the average. And this last one, if you're not careful, is gameable, because I'm not summing over them. I'm looking at the maximum, right? So if you wanted to kind of cheat and make your L infinity calibration error look small, you could just predict things to 1,000,000 decimal points of precision, and it would be small, not because your predictions were accurate, but because the level sets were tiny. Okay, so beware of this last one. Maybe my board planning could have used work. So let's just note that there's a relationship between these quantities. These aren't, like arbitrarily different measures of calibration error that have nothing to do with one another. We will work with whatever one is most convenient for us at the time, but like there's a natural relationship between all of these things. Okay. So what is it? Well, the L2 calibration error is always smaller than the L1 calibration error. And it's not that much smaller. The L1 calibration error is bounded by the square root of the L2 calibration error. And similarly, the L infinity calibration error is always smaller than the L1 calibration error. Which itself is bounded by m times the L infinity calibration error. Okay, where m, remember, is the size of the range. And maybe, I'll just sort of tell you why this is, although the proof is simple and in the notes. But most of this you can understand just by looking at it. So first of all, let's compare the L2 calibration error to the L1 calibration error. So the L1 calibration error is, this weighted sum of these absolute values, right? What's inside the absolute value? It's the difference between the prediction of the model and the conditional label expectation conditioned on the prediction. Now, as we've been doing, we're sort of scaling things so that the labels are between 0 and 1, and so the predictions might as well also be between 0 and 1. And so the thing inside the absolute value here, it's got norm at most 1. Okay, so what happens when we move from K1 to K2? Well, we're just squaring the term and the absolute value. But it's a term that's less than 1. So squaring it makes it smaller. That's why the L2 calibration error is less than the L1 calibration error. Maybe the only one that's worth like working out on the board is the fact that the L1 calibration error is less than square root of the L2 calibration error. And that follows from the Cauchy-Schwarz inequality. So, I guess the Cauchy-Schwarz inequality says something like, if I have two random variables, A and B, the expectation of A times B squared is at most the expectation of A squared times the expectation of B squared. Okay. And so, what can we say? Well, we can write the L1 calibration error as just the expectation over a randomly chosen level set of the sort of marginal mean consistency error on that level set. Okay, so it's like the expectation of some random variable B, which I can think of if I want as the expectation of 1 times B. Okay. So I can write the L1 calibration error as the expectation over a randomly chosen level set V of 1 squared times the expectation times the absolute value difference between V minus the expectation of the label conditional on f of x equals V. Right, all I've done is I've noted that the L1 calibration error is an expectation, and I've multiplied it by 1. And by the Cauchy-Schwarz inequality, this is at most, well, the expectation of 1 squared, that's 1, times the expectation, again, over a random choice of level set of V minus the expected value of the label, conditional on the level set being V squared, which is just the L2 calibration error squared. And then finally, the L1 calibration error is just the sum over all of the level sets of the term that makes up the L infinity calibration error. Okay, so summing up over a bunch of non-negative things gives me only a bigger number. So the L1 calibration error is only bigger than the L infinity calibration error, but the L infinity calibration error is the maximum over the terms, the M terms that we're summing over. So, the L1 calibration error can't be larger than M times the L infinity calibration error. Anyway, that is all to say that depending on our mood, we can measure calibration error in a number of different ways for different applications. Different ones of these may be more or less convenient, but they're all related to one another. Maybe you should be a little more suspicious of L infinity calibration error because it's possible to make that small without knowing anything really about the distribution, just predicting lots of decimal places, but not the others. Okay. Yeah, or at the very least, you have to evaluate L infinity calibration error in terms of m, the size of the cardinality. Okay, so we can measure the squared error of a model. We can measure the calibration error of the model. Note that these two things are a little bit different in kind, in that, it may be impossible to drive the squared error to 0, to find a model that has 0 squared error. The only way to do that is to make deterministically perfect predictions. On the other hand, we know in principle it's always possible to have 0 calibration error as measured in any of these 3 fashions, because the true conditional label distributions have 0 calibration error, just because by definition, if the prediction I'm making V is, always equal to the expected value of the label conditional on X, then, each of these terms inside calibration error is zeroed out. Okay, so it's always possible to make predictions, in principle at least, that are perfectly calibrated. Okay. And let me just remind you of one more fact that we already proved, but it's going to be useful in a moment. And it's that not only do the true conditional label expectations, this thing that we've been calling F star, not only do those have 0 calibration error, those also have the best possible squared error. Okay, those minimize the Breyer score pointwise. And in particular, this is something we've already proved, but let me just write it down to remind you. No matter what distribution on labels we have, so fix any label distribution, dy, and let's say that V star is the actual expectation under dy of the label. And let's say that V hat is some corruption of that. V hat is V star, the true expectation, corrupted by some delta. Then if I look at the expected squared error of the prediction V hat compared to a randomly drawn label, and I compare that to the squared error of the true mean of the label distribution, again evaluated on a randomly drawn error, not only will the true mean have lower squared error, it'll be lower by exactly delta squared. Okay, so we proved this, I think, on the first class. But it's going to be useful here. And note that a corollary of this is that the true, the true conditional, the function that maps each x to f star of x, the true conditional label expectation, will have the lowest squared error amongst all models because it will pointwise minimize squared error for every conditional on every feature vector. Okay. Okay. So here's the question I want to ask and answer. Suppose you give me some model F, and I look at it and I measure its calibration error, and it's got high calibration error. Okay. Can I fix it? Can I calibrate it? So I want to mess with it somehow, maybe similar to how we messed with models in simple ways to get marginal mean consistency, so that after I mess with it, the model is calibrated. But I don't want to make the model worse. Okay, so it would be a shame if I took your complicated model and just replaced it with the constant function that was predicting the mean of the distribution, which would be calibrated, but you might be unhappy with, like, you spent all this time coming up with your clever model, and I gave you back a simple calibrated model that's a constant function. So I don't want to just have a procedure that takes some model and outputs a better calibrated model. That would allow me to do something dumb like output the mean of the distribution. I would like to take a model and output a calibrated model that is better than the model you started with, that has lower squared error. Okay. And so we're going to be able to do that. What we're going to be able to do is something like the following. For any alpha, we can, given a model F, output a new model F hat such that one, F hat will be calibrated, or it'll have calibration error at most alpha. Okay, so first, let's say in this case it'll be, I think, most convenient to work with L2 calibration error. The L2 calibration error of F hat on the distribution will be at most alpha. Okay, so you gave me some model that was perhaps poorly calibrated. You said I want it to be well calibrated for some stringent tolerance alpha. I can do that. And two, I want the model to be better. And in fact, one nice thing about squared calibration error is I'll be able to say exactly how much better it is. Okay, so if I look at the Breyer score of the new model that I give you back and compare that to the Breyer score of the model we started with, well, the Breyer score of the model I give you back should be smaller. So this should be like a negative number. But in fact, it'll be smaller by exactly the difference in calibration error between F hat and F. Okay, so if you gave me a model that was poorly calibrated, then there was no good reason for your model to be poorly calibrated if what you cared about was accuracy as measured by squared error. It's not like there's some bias variance trade-off or something and you could get higher accuracy by being poorly calibrated. In fact, if you're poorly calibrated, you've left an amount of accuracy on the table that is exactly equal to your L2 calibration error, because I have a way of improving your model as measured by squared error exactly by your L2 calibration error. So if you're very badly calibrated, there's a very simple way to just improve the model. And the improvement in squared error is exactly the improvement in calibration error. Okay, and I'll be able to do this by collapsing the range in some sense, like making the model only simpler in that if I look at the cardinality of the range of the new model, that's only going to be smaller than the cardinality of the range of your original model. Okay. So is it clear what our goals are here? Right, so similarly to how we sort of said, okay, if you give me a model that fails to satisfy marginal mean consistency, I'm gonna fix it up. In that case, it was a very simple fix. I just shift it by the correct amount so that it satisfies marginal mean consistency. And in doing so, I improve the error of the model. Here, you give me a model that is maybe not calibrated. if all I told you was that I was going to give you back a model that was calibrated, I could have given you back the mean of the distribution. And, if you spent, 100, GPU years training your model to eke out the, last little improvements in squared error, you might be like very unhappy with me, even though I satisfied the letter of the contract. But that's not what I'm going to do. I'm going to give you a model that is derived from your model and has low calibration error, as low as you like. And in fact, the improvement in calibration error is going to be the same, exactly the same as the improvement in squared error. And so if you, by, running your GPUs for 100 machine years, came up with something that wasn't calibrated, then, here's a simple thing you can do to improve your model right off the bat. Okay. Okay. So let's think about how we can go about improving models that aren't calibrated. Now, remember, when we encountered models that failed to satisfy marginal mean consistency, what did we do? We just shifted them so that they satisfied marginal mean consistency. Now, these measures of calibration error, if you like, are just marginal mean consistency, measures of marginal mean consistency, but not over the whole distribution, but separately on the different level sets of the predictor, right? It's just the average marginal mean consistency error over the level sets of the predictor. And so the obvious way to try to fix them is what we're going to do, which is to, if we find, if the predictor has high calibration error, there must be some level set on which it has high marginal mean consistency error. All we're going to do is fix that level set the same way we fixed entire predictors that had marginal mean consistency error, by just shifting the prediction on that level set without shifting it elsewhere. Okay, that's it. And now, we might have to do it again, right? For marginal mean consistency, it was a one-shot thing. We shifted the prediction overall, and then we were done. Now, like when we shift the prediction on a level set, first of all, there's other level sets we haven't handled yet, but also there's interactions. Maybe I shifted the value and I've merged it with another level set. So I might have increased the marginal mean consistent. I decreased the marginal mean consistency error on the level set I started with, but if I kind of crash it into another level set and merge it with another level set, I might have increased the marginal mean consistency error elsewhere. And so we're going to need to think about things and make sure that we're actually making progress and we're not getting ourselves in cycles. But the basic building block of our operation is going to be this very, very simple update, which just shifts the predictor not everywhere, but shifts the predictor only on a single level set. Okay. So we'll call this a value patch. So given a model, which can be anything, any mapping from features to 0, 1. And any pair of values v and v prime, which are also just numbers between 0 and 1. Let's define this function, which I'll call the value patch applied to the function f for the pair of values v and v prime, which I'll just write as a function of, well, it's still a function of examples x. And what's it parameterized by? Well, the model we started with, and this pair of values v and v prime that I'll write as v arrow v prime to sort of make clear that what I'm talking about is the patch that took the level set that used to predict v that has been shifted to predict v prime instead. So what is this function? It's very simple. It's just the function that predicts v prime whenever the model f used to predict v. That's why we're calling the shift v to v prime, and predicts whatever the model predicted before otherwise. Okay. Is it clear what this value patch is doing? All it's doing is it's completely analogous to this shift by delta that we used to correct marginal mean consistency errors. All it is doing is it is shifting the value of the function from v to v prime on the level set defined by v, right? So whenever the model previously predicted v, we're going to shift it to predict v prime, but we're not going to change the model elsewhere. The model previously did not predict v, then the new model is unchanged on those values. Is that clear? So very, very, very simple update. Okay. And our calibration algorithm is going to be sort of like the simplest thing you can imagine. It's just going to be an iterative algorithm. It's going to say, is my current model calibrated? If the answer is yes, if it's already calibrated up to error alpha, say, then we're just going to pop the champagne and celebrate. If it's not calibrated, if it has high calibration error, then there must be some level set on which it's got a large marginal mean consistency violation, in which case we'll just patch the model on that level set. We'll measure the expected value of the label, the average value of the label on that level set, and we'll patch that level set. And then we'll continue until hopefully we converge. Okay. Here's the algorithm. I'll just call it calibrate. And it takes as input a function f that we'd like to calibrate, a calibration tolerance alpha. We'd like to get the calibration error below alpha. And we'd like this calibration error to be measured on some distribution. For now, I'll pretend we have exact access to this distribution, meaning we can just evaluate expectations over this distribution, but eventually we'll think about running over the empirical distribution of a data set sampled IID from the underlying distribution. Okay, so it's an iterative algorithm. It's going to keep track of some current model at each round. Initially, the model it's keeping track of, it's just the model it's starting with. And the variable little t that we're going to use to keep track of iterations, we'll initialize that at 0. Now, while the L2 calibration error of our current model is bigger than alpha, we're going to go about trying to patch it. If it's less than alpha already, we're done. We can spit out whatever is the current model. What we're going to do is we're going to find the level set on which the current model has sort of the biggest violation of marginal mean consistency, or really, since we're thinking about L2 calibration error, the biggest squared violation of marginal mean consistency. So we'll let VT be the element of the range of our current model that maximizes the product of two things. The size of that level set. We don't want to find tiny level sets. So it should maximize the product of the probability that on a randomly drawn point, we're in that level set, times the squared marginal mean consistency error on that level set times the squared difference between V and the true expected value of the label conditioned on the model taking value V. Okay, so we're finding the level set among, possibly M of them that maximizes the product of the size of the level set times the square of the marginal mean consistency error. And, since the L2 calibration error is large, there's got to be some level set for which this is at least kind of large. And what we'd like to do is we'd like to patch up this model on this level set. It's predicting the wrong mean. So what we'll do now is we'll compute the correct mean on this level set. Right, so it shouldn't be predicting VT here because that's got large error. Instead, what it should be predicting is VT prime. VT prime is just the expected value of Y given that the point X that we drew was in level set VT. Okay, this is what it should have been predicting on that level set if we wanted to have the right marginal consistency, if we wanted to satisfy marginal mean consistency on that level set. And then we'll just update the model by applying this value patch. Okay, so we'll let tomorrow's model, we'll let FT plus 1 just be the result of applying the value patch on model FT, mapping VT to VT prime. Okay, and that's it. We'll run this until it halts when, and if it breaks out of this loop, we'll just output the final model. Okay, is the algorithm clear? It's sort of the first thing you would think of. It just says, are we done? Is there significant calibration error? If there is, there must be a level set on which our predictions are wrong on average. Let's just figure out what our predictions should have been on that level set and greedily shift the model to be correct on that level set. And what we need to prove is two things. We need to prove that, first of all, this thing converges and outputs something. Like a priori, that's not clear. There's a while loop here, right? Like maybe it runs forever. So we need to show that this thing converges. Of course, if it converges and outputs something, like for sure it's calibrated because that's the halting condition of the while loop. It can't halt unless it's got at most alpha calibration error. But we want to prove that, we need to prove this. We need to prove that the decrease in calibration error is exactly equal to the decrease in Breyer score, the decrease in squared error, so that it's not that calibration is some orthogonal goal to accuracy. Like we've in fact increased accuracy by the exact same amount that we've increased calibration, at least as measured by the L2 calibration score. Okay, does that make sense? All right, it's 4:15 on a Friday. Stated the punchline. Maybe we'll wait till next class to prove this theorem. But yeah, maybe the takeaway is calibration is easy to achieve. It is worthwhile to achieve because if you're miscalibrated, not only is that very good evidence that you haven't correctly found the true conditional label probabilities, but why not be calibrated? You can be calibrated and it'll improve your accuracy as well. And then we'll start next class by analyzing this algorithm, proving it satisfies these properties, and doing the same thing for quantiles. Okay. See you guys next time.